Okay, hello everyone. Welcome to the week 11 of the problem solving session for the heat transfer course under the guidance of Professor Dasgupta and myself Kalpita Nath. And we'll be starting with today's session, but as still people are left to join, so we'll be waiting for 5 more minutes for others to join and then we'll start with today's session. So let us wait for 5 more minutes. Okay, so now I'll start with today's session. And first question, like first three question we have over the previous class. Just 1 second. Four questions rather. So on the previous class, these four questions were left to be solved. So we'll first start with these four questions. So let us read out the question number 11 first. So what does it tell about? First one is a large isothermal enclosure is given that is maintained at 2000 degrees Celsius. This outer one. And what we have to calculate? We have to calculate the emissive power of radiation that emerges from small aperture, this object that is left inside of this enclosure. Right. And what is the wavelength below which 10% of the emission is concentrated, and what is the wavelength above which 10% is concentrated, and the emissive power variation with respect to the wavelength for a specific temperature is already provided here. Right. And what the next thing we have to determine is the maximum spectral emissive power and the wavelength at which the emissive power occurs. That this we can directly determine, right, by lambda t is equal to 2898. But before that, we have to understand how to solve this out. And the last question is, what is the irradiation that is incident on the small object that is placed inside the enclosure? Okay, this is the formula that you will be required. Uh, so this is Planck's equation, Planck's law, and obviously this constant values are also given that you can easily use to calculate the emissive power. So I'll give you 5 minutes to solve this question, and if you people are not able to understand how to solve this, then what we'll do, we'll go for a bit of understanding how to solve this. I'll give you a bit stepwise solving process, right? And then you may able to solve it by yourself. So I'll give you 5 minutes first to understand and to try and solve this. Okay, so I'll give you a bit of the details of how to solve this. So first, what they have asked from us is that to calculate the, so we'll go step by step. So first of all, we need to calculate the emissive power of the radiation that emerges from a small aperture, right? So as it is said that it is isothermal, maintained at uniform temperature, and it is an isothermal closure. So obviously from literature we can understand that we can consider this as a black body. So if you consider this as a black body, emissive power, we know that sigma T to the power 4, right? So we can use that equation to calculate the emissive power here. For the next segment, what is the wavelength below which the 10% of the emission, we can use the fraction term by that, the fraction of emission, right? That is the cumulative emission. So that fraction we can use, it's given as 0.1 for the first part, that is up to lambda 1. So if we take that, just one second. See, this is a chart that is already provided. So for what fraction, what will be the lambda t, we can easily get from here by interpolation, right? So first we'll see that what fraction is provided and what will be the corresponding lambda t, that we'll find out by interpolation. And that lambda t temperature is already given for the enclosure, right? And see, temperature is already given here, and as temperature is given, so lambda we can easily find out for both of the cases. Now moving forward to the next question is, determine the maximum spectral emissive power and the wavelength at which the emission occurs. So for this we can use Wien's displacement law. So lambda t, lambda max t into 289 is equal to 2898, right? So by using that, maximum wavelength we can get from there. Next one is, what is the maximum spectral emissive power? Just put the wavelength, that wavelength, maximum wavelength, into this Planck distribution law. The values are already given to you, so you can get the maximum emissive power from it. And what is the irradiation incident on small object placed inside the enclosure? Okay, so obviously it will be equal to the radiation that is being emitted by the whole enclosure, and all that will fall into that small object, right? So this will be equal to that. So yeah, you can easily solve all of them. I'll give you 5 minutes for this, for solving this. I've already told you how to solve, and then we'll proceed with the solutions. I'll just show you how, like what are the values will be. Okay, I think we should proceed with the solution for today's question, the first question rather. So, as I've already said, as it is an isothermal enclosure, so we can take it as a black body radiation. So the first part will be simply using equation for the emissive power for black body. So the emissive power will be for the black body at the temperature that is given, that is sigma T to the power 4, and that will be equal to 5.67 10 to the power minus 8 watt per meter square Kelvin to the power 4 into 2000 Kelvin, that is the temperature of the enclosure, 4 to the power 4. So that will come across 9.07 into 10 to the power 5 watt per meter square. Now, for the part B, the wavelength lambda 1 corresponds to the upper limit of the spectral band for the first part. That is, we have to get all the emission that has occurred below that lambda 1. So the upper bound is lambda 1. So we have to find between 0 to lambda 1, right? Containing all the 10% of the emitted radiation. So it's already given, that is the total cumulative fraction of the emitted radiation is, that is 0 to lambda 1 is given as 0.1, right? So if we go to the table for that fraction, so we can see that 0.1, that is, it's between this and this, right? Just let me mark it up. So this is one bound and we have to just do interpolation in between them. And this is another, right? So what we have to do, we have to do interpolation between them. So if we will do interpolation, then we already know that x1 y1 is equal to 0.066728 and its corresponding lambda t is 2000, and x2 y2 is 0.100888 and its corresponding lambda t is 2200, right? Now we need to find x for which, like y for which x is, just 1 second. So x is 0.1 now, x means the fraction is 0.1 now, and we have to find lambda t, that is the y, right? So y is equal to, we already know, that is y1 plus y2 minus y1 upon x2 minus x1 into x minus x1. So if we will put everything over here, we'll get y to be 2194.8, that is lambda t at f is equal to 0.1. So let us proceed to the question now. So lambda t is equal to 2194.8 micrometer Kelvin. Now lambda 1 into temperature of the enclosure is 2000 is equal to 2195. So lambda 1 is equal to 1.1 micrometer. So this is the first part. Now it said that the wavelength lambda 2 correspond to the lower limit and we have to find up to infinite. So what we can do, like it's given lambda 2 to infinite, the total cumulative emission, right? So this will be 1 minus f of 0 to lambda 2, right? So this is given as 0.1, that is total 10% emission above that. So f, if we find from 0 to that is f 0 to lambda 2, so that will obviously come to be 0.9, right? So if we find 0.9 corresponding, so corresponding to 0.9, we'll take two values. Which one? Let's take this value 1, another one is this value. Okay, these two values we'll take, right? So what we'll do, y is equal to y1 plus y2 minus y1 upon x2 minus x1 into x minus x1, right? So this y1 is equal to 0.890029, y2 is equal to 0.090, sorry, 0.903085, and x2 is just 1 second. Okay. Let's clean this up. I have written wrongly. So x1 y1 is x1 is 0.890029 and this is 9000, and x2 y2 is equal to, this is 0.903085 and this is 9500. So xy is equal to 0.9 y. So you have to find that 0.9, the y value, that is a cumulative the cumulative fraction for, sorry, the lambda t for this cumulative fraction 0.9. So when we'll interpolate it, we'll find that this y, that is, it is 9381.855, and that will be is equal to lambda 2 into 2000. So lambda 2 is equal to 4.69 micrometer. Now, so this we already found out. Now we have to determine the maximum spectral emissive power, and for that we need to first determine the wavelength at which we'll get that maximum emissive power. So that we can do by Wien's displacement law. So lambda max into T is equal to 2898 micrometer Kelvin. Now this is 2000, so lambda max will get us 1.45 micrometer. Now the spectral emissive power associated with this maximum wavelength can be computed from this Planck's distribution. So the emissive power is already given. So this is C1 is already given as 3.742 into 10 to the power 8 upon C2, and lambda is 1.45 whole to the power 5 exponential. C2 is 1.439 into 10 to the power 4 upon lambda is 1.45 into temperature is 2000. So temperature is 2000. This whole minus 1. So this will come out to be what? This will come out to be 411447.7 watt per meter square micrometer. So this is 4.12 into 10 to the power 5 watt per meter square. meter square meter. Okay, now what we have to find out lastly is the irradiation incident on a small object placed inside an enclosure. So as it is already placed inside the enclosure, so all of the radiation will be falling on that small object, right? So the radiation that is incident on that will be equal to the emission of the whole enclosure. So if the radiation that is incident is equal to emission for the whole enclosure, that is the black body, that is sigma t to the power 4, that already we found out earlier, 9.07 into 10 to the power 5 watt per meter square. Okay, this is done. Now we'll proceed to the next question. For the next question, the surface of black body is at 500 Kelvin temperature. So obtain the total emissive power. And also find out the wavelength of maximum monochromatic emissive power. So a surface, the surface temperature is given, so we can use simply for black body radiation the emissive power, and we can use Lenz's displacement law for calculating the maximum wavelength. So this is rather easy, as you have already done in this question already. So I'll give you 2 minutes for solving this. Okay, so we'll proceed with this question. So surface temperature is given as 500 Kelvin. So as we have already done in the previous question, so the emissive power will be sigma T to the power 4. So this will come out to be 3.54 kilojoule per meter square. Second. Right. Now, by Wien's displacement law, we know that lambda max into T is equal to 2898. So lambda max temperature is already given, will come out to be 5.796 micrometer. Okay. Now, let's proceed to the next question. So sun may be considered to be a black body with surface temperature of 5780 Kelvin. Calculate the fraction of total solar radiation that falls in the visible range and the fraction that occurs on the left of the visible range and the fraction that occurs on the right of the visible range. Lambda is also given above and below, which you need to calculate. The wavelength and the frequency of maximum spectral emissive power and the maximum spectral emissive power and the hemispherical total emissive power. You have already done that in the previous question. The similar question was there. So you can easily be able to solve it. So again, you will be using this graph. Or what you can do, you already know the wavelength, right? So from wavelength also lambda t you can calculate. And corresponding to that lambda t, what you will do? You will calculate this fraction f, the fraction of the emission. So that you can do by using this table, right? And this fraction will give you this answer to these questions, and then this Wien's displacement law, and this you will get from the Planck's distribution law, and the hemispherical total emissive power you can get by using simple emissive power equation, sigma to the power 4. Right. So yeah, I'll give you 5 minutes to solve this, then we'll proceed with the solution. Let's see whether anyone answers or not. Okay, so whoever have joined just now, so this question has been provided and 5 minutes was given to solve this. Uh, I've already explained how to solve. So basically, we have already previously solved one similar kind of question, and over there, the fraction of first a black body is given, and its surface temperature is given as 5780 Kelvin, right? Now we have to calculate the fraction of solar radiation that falls in the visible range, that is the fraction of total solar emissions in the visible range is between we already know this, between which of the two wavelengths. So let's suppose now the visible range is between zero point 0.4 to zero point 0.7. So first of all, we have to take the lambda 1 to be zero point 0.4 and lambda 2 to be zero point 0.7, and we have to calculate the fraction between them, and for that we'll be using what? We'll be using this chart, right? So yeah, in this way we'll calculate for the visible range, and now individual also we can calculate in the similar way, cause we already know the temperatures. So we already know the temperature. So as I was explaining, in this question, a black body temperature is given, and its fraction of solar radiation that is falling on the visible range we have to find out. So for that, first of all, what we need to find lambda t for finding the fraction that is falling. So similar question we have already done today itself. So for that we'll be using this whole chart. So for that, for the finding the fraction, we need lambda t. So for getting lambda t, first of all we need to know the visible range. So the visible range is varying between zero point 0.4 to zero point 0.7, as is already explained in the question. So first of all, for the visible range, lambda 1, that is the lower bound, will be zero point 0.4 and the upper bound will be 0.7 for the part A. So in between that, we can calculate the lambda t, and corresponding to that lambda t, we can get the fraction, right? The fraction of the emission in that particular range. Part B also we can solve in the same way. C also we can solve in the same way. And the wavelength and frequency for maximum spectral emission, we can use Wien's displacement law. And for the maximum spectral emissive power, that we can use the Planck's displacement distribution law, right? And the hemispherical total emissive power, there we can simply use sigma t to the power 4. That will give the total emissive power, right? So you try and solve this. If you will need this, because I can't show two slides at a time, so I'll be keeping it aside. When you will be calculating this part, you can simply ask me, so I can shift that to that slide, and then you can solve this. So I'll give you 5 minutes as you've just joined, and then we'll proceed to the solution. If you are unable to understand anything, any doubt you're facing, then you please unmute yourself and ask me the question. Are you solving this, or are you not able to understand? Are you listening? Okay, anyhow, I'll wait for 2 more minutes and then we'll proceed with the solution. And we have one more class left on the next week, and then we'll wrap it up. I may take one extra session. If I will, then you will be informed by mail. Okay, I think we should proceed with the solution. We have waited way too much time for this. So, first of all, Sun is considered as a black body here. So, hence its emissive power can be easily found out by Planck's equation. So, first part is the fraction of solar radiation that corresponds to the range of wavelength in the visible range. That is lambda 1 to lambda 2. That may be given by lambda 1 to lambda 2 1 upon sigma t to the power 4 lambda 1 to lambda 2 e b lambda d lambda, right. So this is fb 0 to lambda 2 minus the fraction of the black body emission 0 to lambda 1, lambda 2 to lambda 1, right. So the visible range in the spectrum covers from 0.4 to 0.2, so this will be 0.7, 0.4 to 0.7, so this will be 0.4. So for 0.4 we need to for finding out the fraction, we first need to calculate the lambda t, as I've already shown in this graph, sorry, chart. So for corresponding lambda t we can get the fraction. So lambda t, lambda 1 t is for 0.4. So temperature is given as 5780, so this is 0.4 into 5780, so this is 2312 micrometer Kelvin. And for lambda 2t, this is 0.7 into 5780, this is 44046 micrometer Kelvin. Now from the table, if we get on with that, so first of all is 2312. So if we will interpolate in between this, there is 2200 to 2400, we'll get that the fraction for 0 to lambda 1 is equal to 0.1229, as I've already shown in the previous question, so I'm not going into the details. You can do it by yourself how to do the interpolation. And this is for 0 to lambda 2, this will be 0.488. Now the fraction in the visible range is f p lambda 1 to lambda 2, that will be is equal to 0.4889 minus 0.1229, so that will be is equal to 0.366. Now for B and C, the fraction of the radiation that occurs in between 0 to 0.4 micrometer, that will be already we have calculated as 0.1229, and from lambda 2 to, that is for the above 0.7, so that will be is equal to f lambda 2 to infinity, that is 1 minus f 0 to lambda 2. So 1 minus this we already know as 0.4882, sorry 889, so this will be 0.511. Now for the next part, the wavelength and frequency for maximum spectral emission. So for this that is part D, this will be simply using means displacement law. So there is lambda max into T is equal to 2898 micrometer into Kelvin. So this lambda max temperature is 5780, so this is 2898 upon 5780, so this will be 0.5014 micrometer. Now the corresponding frequency, how to find the corresponding frequency? The frequency is given by speed of light into, this is electromagnetic radiation, so speed of light into lambda max, the maximum frequency, right. So this is 3 into 10 to the power 8 or 2.99 into 10 to the power 8 meter per second upon lambda max is given as point, like we found out as 0.5014. So this will be 5.98 into 10 to the power 14. Now part E, the hemispherical total emissive power. Oh, sorry, before that, the maximum spectral emissive power we need to calculate, so that we can easily calculate from the Planck's distribution law. So this is 3.742 into 10 to the power 8. This is already given in the previous, we have already solved this, right? So we can simply use this upon 0.5014, that is the lambda max, whole to the power 5 exponential 1.439 into 10 to the power 4 upon temperature, the temperature for maximum wavelength is 2898 minus 1. So this minus 1, sorry. Yeah, so this will be 8.293 into 10 to the power 7 watt per meter square micrometer. So this is 8.293 into 10 to the power 13 watt per meter square meter. Right, and for the last part, the hemispherical total emissive power will be simply, the emissive power is equal to sigma T to the power 4. Sigma is 5.669 to 10 to the power minus 8. Temperature is given as 5780 to the power 4. So this is 6.327 into 10 to the power 7 watt per meter square. Okay, now let us proceed to the last question of previous class. So a small black body has total hemispherical emissive power. It's given as this. Determine the surface temperature and wavelength for maximum emission. In which range the spectrum does the wavelength fall? So this is the similar related question. So the emissive power for the black body is sigma T to the power 4. So use the corresponding, the emissive power is given, corresponding temperature you can find out, and the wavelength for maximum emission we can calculate from means displacement law. So yeah, this is done. Okay, I'll give you 2 minutes to solve this question and then we'll proceed with today's question. So we have taken a lot of time for previous day's question. We'll then proceed with today's question. Yeah, so I'll give you 2 minutes now. If you have any doubt in understanding, you can unmute yourself and ask me the question. I'll just be back in 2 minutes. Okay, let's solve this question. So, as I've already said, that it is a black body, so we'll be using, for the emissive power, we'll be using sigma t to the power 4. So this is 5.669 into 10 to the power minus 8 t to the power 4, and here emissive power is given, so 4 into 10 to the power 3 watt per meter square, right? So here T we will get as 515 Kelvin. And the wavelength of maximum emissive power is, we can get by Lenz's displacement law, 2898. So this lambda max will be 5.63 micrometer. So this wavelength obviously falls in the infrared region, because the visible in the infrared region of the spectrum. So let's proceed to the first question of today's session. Like, this was the previous day's question till now. Now for the first question of today's session, this is a rather simple question. So for an ideal body, black body, which of the following is incorrect? So I think you'll be able to answer this. It is very easy. Which of the following is incorrect? Not correct. Which of the following is incorrect? So what will be the answer? So I'll give you 1 minute to answer me this question, and then I'll tell you the answer. Okay, so the answer for this is, see, for ideal black body, we know that absorptivity is equal to 1, the reflectivity is equal to 0, and also transmittivity is equal to 0, and emissivity is equal to 1. That is, for black body, the absorptivity is equal to emissivity. So that is, everything that is falling on the surface is absorbed, the perfect black body, right? So obviously for this, the correct answer will be D, because transmittivity is not is equal to 1 for black. So let's proceed to the next question.
The value for maximum lambda decreases as the temperature of the black body increases in Planck's distribution law of EB lambda versus lambda lot. So choose the correct option for this. This also I don't think it should take time. So I'll give you 1 minute for solving that as well. Just tell me which of the option is correct. Okay, as no one is answering, so let me answer this question for you. So if we plot EB lambda with lambda, so this we know that for lower wavelength this will be sorry, for lower temperature it will be like this, it will be like this, it will meet at the same point, then it will be like this, that is as the temperature increases the maximum wavelength will gradually decrease, right? That is, this temperature is 3500 Kelvin, this is 4000 Kelvin, this is 4500 Kelvin, this is 5000 Kelvin, and so on, right? That is, as temperature increases the lambda max decreases. So this option is true, that is option A. Now let us proceed to the next question. For a gray body, the values of absorptivity and emissivity are less than 1. So choose which of the following is correct for this statement. I'll give you 1 minute for this as well. Answer me which of the following is correct, that whether this statement is true or it is false. Uh, so I'll draw a diagram and then I'll explain. So if we plot E lambda to lambda for black body, gray body and real body, it will be like this. Like this is for black body, this is for gray body, and this is for real body. Black body, it will be having maximum. This is gray body and this is real body. That is for any given wavelength lambda 1. This is E lambda 1, this one, and this is E lambda 2 for this. For gray body, E lambda upon E B lambda 1. So E B lambda 1 is equal to epsilon lambda. For gray body, gray body is such kind of body for which the monochromatic emissivity does not depend upon wavelength. That is, at lambda 1, lambda 2, everywhere this will be same. This will be constant for gray body. That means that this will be constant. That is, E lambda 1 upon EB1 is equal to EB lambda 1, E lambda 2 upon EB lambda 2, and so on will be same for gray body. E lambda is constant at a given lambda, epsilon lambda. So if we plot epsilon lambda to lambda, this is 1 for black body, and for gray body this will be less than 1, and for real body it will be somewhat like this. It will vary. For gray body it will be constant. This is gray. So obviously for gray body, alpha and epsilon will be less than 1. That is, emissivity and absorptivity both will be less than 1. So option A, that is true. Now let us proceed to question number 4. Consider both statements. Even if one of them is wrong, then mark the answer as false, else mark it as true. For a black body, radiosity is different from the emissive power since a black body reflects all the radiation incident on it. The spectral intensity for emitted radiation can be defined as the rate at which the radiation energy is emitted at a wavelength lambda in the theta phi direction per unit area normal to the direction per unit solid angle about this direction. So tell me whether both of the sentences or statements are true, then we'll mark it as true, otherwise we'll mark it as false. So I'll give you 1 minute to solve this as well, and then we'll proceed with the solution, like which one of the options are correct. I'll be back in 1 minute. Okay, so we know that radiosity J is equal to total radiation that is emitted plus total radiation that is reflected. That means radiosity is total radiation that is leaving the surface. Now, a black body absorbs all the radiation incident on it. It does not reflect, it absorbs. And there is no reflected component on the radiosity. Right? So, thus, in a black body, it is, yeah. So, in a black body, radiosity is equivalent. See, for black body, this one will cancel out, right? So in a black body, the radiosity will be is equal to the total radiation that is emitted. Cause the reflection is not there, because everything that is falling on the surface will eventually get absorbed. So that's why this first statement is wrong itself. So it will be false. Let us proceed to question number 5 now. The spectral emissive power E for a diffusely emitted surface is defined as the following. That is, for lambda less than, that is the wavelength less than 3 micrometer, the emissive power is 0. From 3 to 12 micrometer, it is 150. And from 12 to 25, it is 300. And greater than 25 also, it is 0. So what is the total emissive power for the entire spectrum? This is very easy. Like it will take 2 minutes for you to solve. So I'm giving you 2 minutes for solving this, and then we'll proceed with the solution.
Okay. So for the spectral emissive power of the surface over an entire spectrum, what we'll do, we'll just one second.
We'll just integrate over the whole spectrum. But since for every range of wavelength, the emissive power is different, so we have to integrate in bits, right? Uh, in whatever range it's given, we have to use that emissive power for that range. So from 3 to 12, it's given like it is one range. So we'll use ED lambda. From 12 to 25, it is one range, and others are 0, right? So from 3 to 12, it is 150, and from 12 to 25, it is 300. So this will come about 5250 watt per meter square. Yeah, so this is option D. For question number 6. Okay, so in question number 6, there is a small metallic ball sphere that is opaque and diffuse coating that have absorptivity of 0.8 for wavelength less than 5 micrometer, and for greater than 5 it has absorptivity of 0.1. So we'll use that values wherever required. The sphere, which initially is at uniform temperature, that is sphere surface temperature is 300 Kelvin, and for initial condition only we have to find everything, and it is inserted into large furnace. So furnace is another surface that is maintained at 1200 Kelvin. So determine the total hemispherical absorptivity and emissivity for the coating for initial condition. The equation that you are going to use are given over here for absorption and emission both. I'll explain you everything, but you first take 5 minutes for solving this, for understanding how and like how you're going to solve it. There are two conditions being given, and this condition, that is this fractions, uh, this fraction of emissive power, that is like the emissions, it's given from 0 to lambda wavelength. It's given for the larger body, right? It's given for the larger body, so will be like basically here our point of focus is the small body, right? So when we'll be calculating the absorptivity, will everything that is coming from the furnace, that will be absorbed by the small body. So we'll be taking the temperature for the furnace, because the emissions that are coming from the furnace, or the reflection, or the radiation, that is basically radiation, what is better, so radiation that is coming from that furnace will be absorbed by the smaller body as per its absorbance based on its wavelength, right? So while finding the absorptivity for the small body, we need to consider the furnace temperature into consideration, right? Initial temperature. And when we'll be finding emission, at that time we'll be considering the temperature for the body itself, the smaller body itself. So for the first one we'll be using for the first case for finding absorption, and the second one, that is the second equation that we'll be using for the second part, that is for finding emission, right? Emissivity, that is. Okay, and the equations are given for absorption and absorptivity and emissivity as it is, and this fraction, remember, it's given for the larger surface, that is the furnace temperature, the larger surface. So we'll be using as it is. How to convert the irradiation, that is G, into the emissive power, I'll be explaining you that, but you first take 2 to 3 minutes to analyze how you're gonna solve it, right? After that, I'll tell you how to solve, and then gradually we'll be solving it as well. So this is a very important question that will solve very basics of your understanding about this radiation, this emissive power, how the fractions will be like the total cumulative fraction, not fraction, rather the cumulative radiation for up to specific wavelength, how you will be using that to solve the corresponding emissivity and the absorptivity. Okay, so I'll be waiting for 2 minutes first. Okay. Uh, First of all, let us have some basics of this. So, the cumulative fraction for emissive power for any specific wavelength can be written as the emissive power for that wavelength to the whole range. So, this gives the fraction of the emission up to that wavelength to the total emission, right? So if yeah, so if we want to find for let's suppose for a black body 5 to 10, that is wavelength from 5 to 10, we have to consider up to 10, and then we'll negate the up to 5 from 0 to 10 and 0 to 5, right? In the same way, if we want to find for the real body, so that is 5 to 10, though, so this can be done by emissivity for that specific wavelength, that is 10, minus emissivity 0 to 5 into fraction of total emission in that specific wavelength range. Now, by Kirchhoff's law, this emissivity is equal to absorptivity. So, we can just replace it with absorptivity, right? And here, as there are two ranges, so we'll divide for everything. We'll be dividing the whole range, that is from 0 to infinity, into two parts. Now, see, for the first equation, the absorption can be written as 0 to see. The absorptivity can be written as, it's already given that absorption in that specific wavelength into G, d lambda in the whole range, this total irradiation d lambda. Now, the total radiation that is falling from this big furnace to that small body, everything will be absorbed as per the absorptivity of the small body, right? So this absorption, the thing that will be absorbing by this body, will be depending upon the emission of this big furnace. That's why we'll be considering on the, as I've already explained, we'll be considering the emissive power for this whole bigger enclosure, that is bigger furnace, right? So here G can be replaced by EB at the temperature is 1200 on specific wavelength. So what we can do now for calculating the absorptivity, the equation that is given is alpha lambda at lambda G lambda d lambda 0 to infinity G lambda d lambda. So it can be simply written as I've already explained, absorptivity in the specific wavelength E lambda B lambda 1200 d lambda. Okay, so this is 0 to infinity EB lambda d lambda, that means it's equal to EB at 12. This can be simply replaced by that. So now this whole range will be subdivided as per the because there are two absorptivity, right, on the two specific range. So we'll just divide it into that two wavelengths. So one will be 0 to lambda 1, and that will be alpha lambda 1 E lambda B lambda 1200 d lambda. So this is constant in that range, right? So it will come out of the integration. So EB 1200 plus alpha lambda 2 lambda 1 to infinity. This is E lambda B lambda 1200 d lambda. This is EB 1200. Now this is the whole fraction, that is up to that range, as I've already explained here. Here I've already explained, right? This can be replaced by this. And we have already seen that the fraction of total emission up to that wavelength can be replaced by, up to that wavelength, how much emissive power is there upon the emissive power on the whole range, that is the total emissive power. So we can simply replace by it. So this is basically the fraction of the emission up to that wavelength. So this is from 0 to lambda 1 plus this is lambda 1, this is alpha lambda 2, this is 1 minus 0 to lambda 2, because this is lambda 2 to infinity, right? Lambda 1 to infinity. This is from 0 to lambda 1. So now from the given data we have lambda t is equal to 6000. When lambda t is 6000, av 0 to lambda is given as 0.738. Temperature is now we'll be considering for the large furnace, so this is 1200, right? So if the temperature is 1200, then lambda will come out to be 5, right? So if lambda is 5, alpha is equal to for lambda up to lambda 1 up to 5, there is lambda 1. For lambda 1 up to 5, lambda 1 up to 5, we have value for alpha lambda 1, that is equal to 0.8. And this fraction is for the large body, that is the furnace, and this is given as 0.738 plus this is given as 0.1 and this is 1 minus 0.738. So this will come out to be 0.6166, that is approximately equal to 0.62. Now similarly, the total hemispherical emissivity can also be found out. So this will be for the small sphere, right? So that, because that is the point of consideration, we have to find for emissivity for that body only. So this is 0 to infinity e lambda b, it's already given in the question, d lambda. So this is EB ds. Now since the surface is diffuse, so we have E lambda is equal to epsilon lambda is equal to alpha, that is the emissivity is equal to absorptivity for that wavelength. Now we can simply replace it by the similar way as we have done in the previous part. So 0 to lambda 1 E lambda b, but this time this will be for the small body, that is lambda at 300 d lambda. This is EB 300 plus alpha lambda 2, this 0 to lambda E lambda b lambda 300, sorry, this is lambda 1 to infinity d lambda upon EB 300. So this will be is equal to alpha lambda 1 f 0 to lambda 1 plus alpha lambda 2 f 1 minus 0 to lambda 1, right? So this will give us what? So second part that is given, it's second part that is given, that is for the given for the small body. This fraction is given for the small body, right? So this temperature we are considering for small body, so this will be 300 and this is 1500, so lambda will again come to be 5. So this will come to be 0.8, this is 0.014 plus 0.1 into 1 minus 0.01. This will come out to be 0.1098, that is approximately equal to 0.1. Okay, so there is a second part for this question. Determine the total hemispherical absorptivity and emissivity of the coating for final steady state condition. So what will be that? I'll give you 1 minute for solving this, and then we'll proceed with the solution. Okay, so for this, because of the spectral characteristic of the coating and the furnace temperature remains fixed, so there is no change in the value of alpha with increasing time. So absorptivity will be remaining same only. But as the TS increases, that is the surface temperature of the absorptivity, because it depends on the bigger furnace, right? So for the furnace it's same, so absorptivity will be same, but emissivity will change. So as the surface temperature for the smaller body will be increasing with time, so after sufficiently long time, as the temperature of the surface of the body will be reaching to temperature of the furnace, the emissivity will be finally attaining the value equal to absorptivity, that is 0.62. Okay. Now, let us proceed to the next question. This will be the last question for today. The rest of the question will be solving on the next week. So, what is said in this question? A liquid oxygen is of boiling temperature minus 182 degrees Celsius is to be stored in a spherical container of 30 centimeter diameter. The system is insulated by an evacuated space between the inner space and the surrounding 45 centimeter internal concentric sphere. For both the spheres, the emissivity is 0.03 and the temperature of the outer sphere is at 30 degrees Celsius. Estimate the rate of heat flow by radiation to the oxygen in the container. So the heat flow by radiation we need to calculate, and also we need to determine the rate at which the liquid oxygen would evaporate at minus 182 degrees Celsius. Latent rate of oxygen is provided here. So yeah, I'll give you 2 minutes. There is nothing to explain this very easy question. So we'll just be using the equation that we have already derived in class. So first of all, you find out the like what surface, how much fraction of surface 1 is exposed to surface 2. That's the inner surface 2 is exposed to the outer surface. And with that, we can find out like the total resistance for radiation. So if we remember the formula correctly, so this Q12 will be is equal to A1 sigma T1 to the power 4 minus T2 to the power 4. Now this is 1 minus epsilon 1 upon epsilon. This is emissivity for first surface. This is the This is fraction of surface exposed for the fraction of the surface that is exposed for the to the surface 2 by the surface 1, and this is 1 upon epsilon 2 upon epsilon 2. This is A1 upon A2. So this we can clearly calculate from the dia. This we can calculate from the this is already like, as it is concentric sphere, so this will be obviously 1. Now epsilon 1 and epsilon 2 are already given, the temperatures are also given, so Q can easily be calculated, right? And if Q can be calculated, then that Q that is coming from like traveling from the, see, outside temperature is high, so heat will travel from outer surface to inner surface, right? So we'll eventually get a negative sign on the heat transfer. So the temperature, the rate at which heat is moving from outer side to inside, at that rate only the oxygen will evaporate. The rate will be same if there is no energy loss, right? So that Q what we have found out will be is equal to the flow rate into the rate at which it will evaporate into lambda, that is latent heat of oxygen. So we can calculate the rate of evaporation from there. So I'll give you 2 minutes for calculating this, and then we'll proceed with the solution. So the view factor in this case, obviously you've understood, right? Because the inner surface, that is surface 1, is totally exposed to the outer surface, the view factor will obviously be 1. So we'll wait for 2 minutes and then we'll proceed with this solution of this last question.
So as I've said, we'll already be using this equation for finding out uh, the rate of heat flow by radiation. So for that, first of all, let us find A1 upon A2. That will be D1 upon D2 whole square. So we can directly put it, and T1 will be minus 182 plus 273. We have to convert it in Kelvin. So 91 Kelvin, and T2 will be is equal to 30 plus 273 is equal to 303 Kelvin. Now area for the surface 1 will be is equal to 4 pi r1 square, that is equal to 4 pi 15 upon 100, because this is in centimeter, whole square, this is 0.282 meter square. For surface 2, it's not like here only area 1 is required. Yeah. So now we'll just put all the values. Q12 is equal to 5.67 into 10 to the power minus 8, 91 to the power 4 minus 303 to the power 4 into 0.282 upon 1 upon 0.03 plus 30 by 45 whole square 1 minus 0.03 upon 0.05. So this will come out to be 2.802 watt. As the flow is from outside to inside, that's why this minus sign is coming. Now, as I've already said, the heat flow that is coming from like due to radiation from outer surface to inner surface, that will only be responsible for the evaporation of the liquid, as there is no heat loss indicated in the question. So this will be utilized, that is 2.80 will be what, that is joule per second, right? This will be utilized in the evaporation of the liquid oxygen. So m lambda, so lambda is given as 215 into 10 to the power 3 joule per kg. So joule will cancel out, so m dot will be is equal to 2.802 upon 215 into 1000. This is in kg per second, but I want to convert it like we want to convert it into R. So if we want to convert it into R, this will be 3600. So this is point. Okay, so this will come out to be 0.0469 kg per R. This is the rate of evaporation. Okay, now it's already 9:20, so we'll be ending the class today here. I'll show you the questions. 3 questions are left. I'll show you the questions and we'll try and solve that in the next week. I'll give you this 3 question as homework. You try back at your home. Most probably we'll be having an extra session in this week as it is, because next week we'll be having the last class for this problem solving session. I hope you all will be remaining present, and let me scroll down the questions. You can take the screenshot, or you can click an image of this. This is the first question. This is the second. This is the third. I won't be explaining these questions in detail. I hope you'll be trying this at your home, and we'll be discussing the solutions in the next week. Okay. Just 1 second. Okay. Thank you for attending the class. I'll meet you in the next session. If an extra session will be there this week, then I'll meet you in that. Otherwise, we'll be meeting in the last session. That will be next week, same time. Okay, bye.